Hello students, in this video we will discuss another method which is solvable for x. This method is used to solve a ordinary differential equation whose order is 1 but degree is not 1. This method is applicable when given equation is of first degree in x only. It means the term x appears with the degree 1, then given equation can be written as x as function of y and p. So if given equation can be written as in this form, we can apply this method which is solvable for x. In this method, now we will differentiate this equation number 1 with respect to y. So we get dx upon dy in left hand part, and in right hand part we get some derivatives of a function of yp, which is represented here with some function phi, as phi is function of y, p, and dp upon dy. Dx upon dy can be written as 1 upon p. So we have another equation which can be derived by differentiating given equation 1 with respect to y, which is 1 upon p is equals to phi of y, p, and dp upon dy. This is an equation in two variables y and p, which gives us a solution which is capital F function of y, p, and c. Now from this equation number 2 and equation number 1, we will eliminate p and get a relation between x, y, and c, which is a required solution. Now we are here, the important thing is we are to eliminate p from the obtained solution which is in y and p, and from the given equation, after eliminating p, we get a resultant relation between x and y, which is a required solution. Now let's try some problem. Here we have y is equals to 2px plus p square y. This here x appear in degree 1 only. So here we can apply this method which is solvable for x method. So here we can find the value 2x is equals to minus py plus y upon p. Now we will differentiate it with respect to y. So we get 2 dx upon dy is equals to minus. Now we are to differentiate it with respect to y. So when we differentiate it with respect to y, first we get minus p. Then we get minus derivative of p is dp upon dy into y. Now we are to differentiate it y upon p. So when we differentiate it with respect to y, first term we get 1 upon p, and second term we get minus 1 upon p square dp upon dy into y. Dx upon dy is what? 1 upon p, so it becomes 2 upon p. Here in right hand part also we have one term 1 upon p, so when we simplify it, 2 upon p and 1 upon p, in left hand part we get 1 upon p. Now shifting this p into left hand part, so we get 1 upon p plus p, and from here taking dp upon dy common, so we get minus y into 1 plus 1 upon p square dp upon dy. Now in left hand part taking p outside, so here we get 1 and here it becomes 1 upon p square. So in left hand part we have p into 1 plus 1 upon p square, whereas in right hand part we have minus y into 1 plus 1 upon p square. So in both terms we have 1 plus p square, so these both cancel out. So it becomes p is equals to minus y dp upon dy, which can be written as dp upon p plus dy upon y is equals to 0. Now we will integrate it. So integration of 1 upon p with respect to p is log p. Similar integration of 1 upon y with respect to y is log y is equals to log c, which is an arbitrary constant. So from here we get py is equals to c, or we can rewrite it as p is equals to c upon y. Now we will use this relation in 1 to eliminate p. So putting the value p is equals to c upon y in given equation, so here we will replace p with c upon y. So equation 1 become 2x is equals to minus c upon y into y plus y square upon c, or after simplification it becomes 2cx minus y square plus c square y is equals to 0. So this is required solution for given problem. Let's try one more problem. Here we have p cube minus 4xyp plus 8y square equals to 0. Now again here x appear with degree 1 only. So here we can apply this method which is solvable for x. If suppose here x appear with some other index like x square or x cube, we cannot apply the second this method which is solvable for x. So for when we solve it for x, from here first we have to find the value of x, which is x is equals to 1 upon 4 p square upon y plus 2y upon p. Divide whole equation with 4xy, we get this equation. Now we will differentiate equation 1 with respect to y. So in left hand part we get dx upon dy, which is 1 upon p. Here 1 upon 4 is constant. Derivative of p square is 2p dp upon dy, and 1 upon y as a coefficient. And derivative of 1 upon y is minus 1 upon y square, and 1 upon 4p square taking as coefficient, plus derivative of y is 1, so it becomes 2 upon p, and derivative of 1 upon p is minus 1 upon p square dp upon dy. Now from here 1 upon p and 2 upon p, so in left hand part we have a term minus 1 upon p, and in these two terms taking dp upon dy common, so we get 1 upon 2 p upon y minus 2y upon p square dp upon dy, and this is the remaining term which is minus 1 upon 4 p square upon y square. Taking this term into left hand part, we get 1 upon 4 p square upon y square minus 1 upon p is equals to half p upon y minus 2y upon p square dp upon dy. Now in left hand part we will take 1 upon 2 p upon y common. So in first term we have a term p upon 2y, whereas second becomes minus 2 upon y upon p square. So this is just common as in right hand part, so these both cancel out. So here we have 1 upon 2 p upon y is equals to dp upon dy, which can be written as dy upon 2y is equals to dp upon p. Now we will integrate it both sides. After integration we get half log y is equals to log p plus log c, or it can be written as log y square log pc. Actually this is not log y square, this is 1 upon 2 and this is log y, so it becomes a square root of y, so it becomes y raised to power half. So here y raised to power half is equals to pc, so from here we get p is equals to y raised to power half upon c. Now we will replace this value in given equation, and according to which we get some different solution which appears here actually. Now here we will replace p as y raised to power half upon c, then we can get required solution. So that's all about this method. Thank you.